continue this session with two speakers, Péter, Isza, and Róbert, Csordás, and they're going to be presenting on an ECG card, open source.
Hi. So we're the MobilECG team, and our goal is to make clinical-grade electrocardiography accessible and affordable for everyone. This is why we're developing an open-source electrocardiograph, and we find this topic so important that we actually need two presenters for this. So this is our device. We're developing both the hardware and the firmware are open source. This is a wearable device that supports all the clinical standards, everything that is important in clinical practice in terms of ECG. It operates with a single AAA battery, and what you can see here is the 3D printed prototype. If you want to visit the GitHub, it's on the top, or a web page. So I'm one of the engineers, and I'm going to talk about some of the principles of electrocardiography, and then Róbert is going to talk about the technical parts, the implementation, so how we did the whole thing. When the heart contracts, the electrical signal is started from the sinoatrial node in the atrium, and a so-called depolarization wave propagates through the heart, continuing from the atrium to the ventriculum, and this wave creates an electrical field that is changing, and it manifests in a voltage signal that can be measured between the different parts of the body. The two hands. Here you can see our very cool ECG business card that measures here in the image the voltage signal between the two hands of my girlfriend, and also you can see the pulse there. By the way, this little card ECG is also open source. If you go on GitHub, you can see the schematics and the firmware. This signal that is measured between the two hands is called lead 1 in the ECG terminology. And it's a real small amplitude signal, just 1 millivolt in amplitude, and a very short duration depending on the heart rate. The hard thing about this, about measuring it, it has a very large DC level, a lot bigger than the signal itself, 300 millivolts. So in order to implement an ECG, you need to remove that so-called baseline. And you usually use a high-pass filter for this. Older designs do this in the hardware. Newer designs do this in the software, just like ours. Okay, so far so simple. If you look at a medical ECG record, you can see 11 more signals than just the lead 1. So let me show it to you here, actually. So this little thing is our device that's completely open source. We believe that, to our best knowledge, this is the only 12-lead Holter ECG in the world that is open source and medical grade. So let me connect this to a patient simulator. So this is the patient simulator. It's a lot bigger than the device, actually. And on the tablet, you can see the ECG curve. Róbert, can you just turn off the simulator, please? And with a little bit of delay, the patient will like die. Okay, okay. So it's an Android app and it's connected via Bluetooth. But the device itself also supports recording, which is really important in medical practice. Let me explain those curves a little bit, then I will get. So this is the standard configuration where you have 10 electrodes, and one of them on the right leg, near the right leg, is just a reference point. That one is the furthest from the heart. Between the other 9 electrodes, you measure 8 voltages, and you calculate 4 other signals from those 8 voltages with a simple linear combination. So that's why it's called 10 lead. There's a concept called Wilson's central terminal, which is the average potential between which is an imaginary point with a potential that has the average of the potentials of the limbs. And all of the voltages are measured against this imaginary point, the WCT, at least almost all, because leads 1, 2, 3 are just simple voltages between the limbs, and the so-called augmented limb leads are the ones that are measured against this central point. Then you have the chest leads, again measured to the WCT point, and these are very important in diagnosing ischemia, which is a precursor to heart attack. So again, you have the 3 limb leads, you have the 3 augmented limb leads, and then from V1 to V6, the chest leads. So this is what you see here. The most common noise artifact comes from the 60-50 hertz mains interference. This is due to capacitive coupling from the wires in the walls. And this results in a very, very big common mode voltage, which is usually really huge compared to the ECG signal itself. Like, for example, it's 1 volt instead of 1 millivolt, which is the amplitude of the ECG. So you need a really, really high common mode rejection ratio, and you still get some noise on the signal. So typically you need a notch filter to remove this noise. The other principle used in almost all biopotential applications is the so-called right leg drive, which what it does is it takes the average of the signal, which is the common mode voltage, and it drives the patient's right leg in the opposite direction from the center. This can result, with this method you can achieve a really, really low common mode voltage. Okay. So now Róbert is going to talk about the technical part a little bit.
Hello. I will talk about the hardware details of the ECG and how to construct a simple ECG. I will explain it through the sample of our business card, which is a simple 1-channel ECG. The concept for the real device, which is 12-channel, is also the same, but obviously it's more complicated. To make an ECG in its simplest form, you need only a high-resolution ADC. That's the heart of everything. We use the ADUC microcontroller, which has a built-in 24-bit sigma delta ADC, and it's basically an ARM core. It has a small LCD and runs from a small battery. And here you can see the block diagram of the device. It's basically the ADC connected directly to the arms of the patient. It only needs some input protection and some biasing to do this, and all the processing is done digitally in the microcontroller. Here you can see the schematic diagram of the device. In the upper left part, you can see the input protection. The upper part is the biasing, which is driven by the DAC of the microcontroller, and the lower part is the ADC input of the controller. There is some buffering because we need that for the low power shutdown mode of the card. And the only other interesting part is the power switch you can see on the left lower corner, but I will not talk about this in this talk. You can see it on our GitHub if you want to. The interesting part of the system is the firmware. It does the whole processing of the analog signal. It basically begins with an ADC driver that gets samples of the signal from the ADC. And the first thing that it does, it filters out the baseline and the 50 Hz noise. The filtering part is a bit tricky. I will explain it later, but it's basically done this way to reduce the computing power needed for this to do the computation. When the signal is filtered, it's displayed on the small screen of the device and also sent to the QRS detector, which basically detects the spikes in the signal, and its purpose is to calculate the heart rate in this project. Now for the filtering. There are two main types of digital filters. The first one, which is most commonly used, is probably the FIR filter. It has the advantage that it has a linear phase. Linear phase means that the shape of the signal is not distorted by the filter, of course, except the frequency band that is filtered out. If the phase is not linear, it means that as the signal passes through the filter, the different frequency bands of the signal propagates through the filter in different time. So the signal won't appear for the naked eye as its input signal, but it will look very weird. And it basically destroys the diagnostic features of the ECG signal. So we cannot allow this. The problem with the FIR filter is that it has many coefficients, which means that for every input sample, you have to run a MEC operation for every of its coefficients, which for high slope filter like this, what we need, can be easily in the range of thousands, so it's very slow. In the contrast, there is IIR filtering, which is basically only a polynomial computation. So it's very fast, but its phase is not linear. So we have to do something with this. There is a trick with which we can make the IIR filter appear as linear filter. The trick is that you need to filter the signal 2 times, once in a forward direction and once in backward direction. If you do this, the phase of the filter cancels out and its phase becomes linear. You basically need to run the backward computation for every block you calculate. But if the blocks are big enough, you will end up with much less computational operations than with a FIR filter. It's obviously slower than one pass of the ER filter in a forward direction. And the algorithm is basically that you get a sample, filter it in forward direction with an IIR filter, and put it in a buffer. And when the buffer gets full, you run the IIR filter in the backward direction on the whole buffer. First get the last sample from the buffer, and so on. Obviously, these operations must be done in blocks, and the blocks must overlap, because there is some time needed for the filter to settle down and stabilize. Other interesting part of the project is how the QRS detector works. Probably the most simplest form of the QRS detector is shown here, but it's still used in real clinical products in this form. First, I like to point out that this is only an illustration, and if you run it in real life, the signal is first rectified, and then are these computations done. But it's much more confusing if we draw a rectified version, so I explain it in this way. So the idea is to use an adaptive threshold to find the local maxima in the signal. And when the threshold crosses the signal itself, then local maximum search is done. And when the maximum is found, then time period is masked out from the signal. This is needed because if you rectify the QRS, then in some time it might happen that multiple spikes appear in the rectified signal, and you need to count these only once. So you need to add some thresholding for this. And when this masking period ends, then threshold is decreased linearly in time, and when the next crossing point is found, then the whole thing runs again. And the slope of this threshold curve and the width of the masking window is calculated based on the heart rate, which can be calculated from this. So it's little feedback in there. Now I will talk about the main hardware in a few words. You can visit our GitHub if you are interested in the software and the hardware construction of the device. And the heart of the device is a complete ECG front end called ADS 1298 from the Texas Instruments. It's basically a whole analog front end for ECGs with 8 24-bit ADC channels. They are all differential. It supports hardware calculation of VCT and RLD leads, and it has basically a serial data output. So it's very easy to use and to design with. The hardware is based on this chip and STM32 main processor, which is a low-power Cortex M4 processor. It also has a Bluetooth module that is from Texas Instruments. This is the least open part of the project. It's basically a closed source library that you can link to their project free of any licenses. The firmware is based on FreeRTOS and is designed only with the help of free and open software like KiCad and GCC. And this is the main part of the schematic diagram of our main device, and the power circuit and the USB part is not shown here. I won't explain this in details, but if you have any questions, I can help you after the talk. Now, thank you for your patience, and feel free to ask any questions.
So what the question? The question was, what's the battery life? It depends on the configuration. So the 12-lead configuration has a little bit more than a day, if you just want to record it. If you want to send it over via Bluetooth, then it's a little bit less. The best battery life you can get is when you have only one channel of ECG, and that is more than 5 days. Yeah, any other questions?
I was wondering, why is threshold adaptive? Why do you need to slope it down?
Okay. So it's an adaptive kind of QRS filtering. But Robert, do you want to answer?
I don't hear the question.
The question was, why do you need to slope down the threshold in the QRS filter?
It's because the amplitude of the QRS complex is not stable. It can be changed very quickly in time. So if you use only a fixed threshold, then it can be easily either the QRS can be missed, or it can be triggered also with the T, the second biggest part of the signal. So you really need to calibrate the threshold to the highest point of the signal locally.
Okay, but I was wondering, so the baseline signal is very large and fluctuating. So is that the reason that you need to know? It isn't.
At the point when the QRS detector runs, the baseline is already filtered out. So
okay.
The first, the IIR filter, which I talked about, is before the QRS detector. So the baseline is removed when this detector runs. So it basically sees a straight line of the ECG. If you move and or move the electrodes, then you introduce some noise. But it's very hard if at all can be filtered out. So when you are steady and the ECG is running, then the QRS detector receives a straight baseline. So you don't have to worry about the baseline wandering.
Hi guys. Why you decided to make your project open source? Is it kind of fun? You're going to make it mass product? You're going to make it commercial or something like this? Is it licensed product or something? If you.
So our main goal is to make electrocardiography accessible and affordable, but yes, there is a business model behind the whole thing. And even though we are planning to sell the device at its production cost, we still think that we have a method to earn money based on from the services, from the online services we provide. It's a freemium kind of business model. People tend to like this thing. We already have more than 2,600 subscribers on the homepage, including a lot of healthcare professionals and a lot of patients too.